maybe try to get going here. And now this is the official start signal from the organizers that we can start recording for everybody. So thanks again for coming back to part 2 of this 3-part on the 2030 mitigation challenge, really looking at methane as one of Canada's key issues to deal with from a policy perspective for reducing emissions in the future, and how science-based research and work can really help hopefully support good policy making in the future, decision making from different types of stakeholders, all the way from industry to maybe the federal government. This afternoon, it's a bit more focused on oil and gas specifically than the morning session. But as you can, appreciate, that's one of the key topics to deal with in Canada when we talk about methane, oil and gas. You can see there's a lineup. We'll have 3 talks of 15 minutes each. I'll just show up in the screen a minute or 2 before the end to signal to the presenters that, it's time to come to an end. Then we have 2 quick presentations for future posters you can see in the Gather Town again, and then 3 more presentations at the end. And I would just suggest to people that have questions, if you have something, don't hesitate, put it in the chat. I'll try to monitor the chat, and if there's a time for a question at the end, you can also raise your hand so we can go through the questions. And maybe if your question hasn't been answered, we might just put this to the very end of the session, and hopefully all the presenters will still be there. And without further ado, I'll give the word to Alex Pletnyov, who will talk about improving detection accuracy in oil and gas. So over to you,
Thanks,
Alex.
Felix. Yeah, I'll share my screen here. Let me know if you can see it.
Yep, this works well.
Okay, so my name is Alex. I'm the CEO of VITAS Consulting Services. We have prepared this presentation in collaboration with our academic partner, SAIT. We provide computer modeling software and consulting for the oil and gas industry. We specialize in computational fluid dynamics. Specifically, we model fluid and gas behavior in storage tanks like the ones you see in this photo. Methane emissions is the 2nd largest cause of global warming today. And needless to say that this is one of the hottest topics today, and a lot of world-leading scientists and organizations are working on this problem right now. Recent studies indicate that fugitive methane emissions from petroleum storage tanks make a significant percentage of vented emissions from upstream oil and gas facilities, and are often unreported. And as you may already know, the Canadian government has mandated a 39% reduction in methane emissions by 2025. And in order to find effective ways to reduce emissions in storage tanks, first we need to accurately measure and quantify them. And this is what this presentation is about. Now I'd like to give you a brief overview of the existing technologies for measuring and monitoring emissions from oil storage tanks. In recent years, technologies for detecting and measuring methane have gone long ways. There are a lot of cool technologies out there, and these technologies can be divided into 2 different groups. Group 1 is physical measurement of fugitive methane emissions using various sensing technologies. Usually they would be installed outside on the tanks. Group 2 is estimations and computer modeling, and that's what we do as well. Each one of these groups has their advantages and disadvantages that I will talk about in the next 2 slides here. So Group 1, basically these are physical sensors that are used for monitoring leak detection and repair. Usually they're installed outside on the roofs of the tanks. It is amazing how far all these technologies have gone in the last decade. Very cool technologies. Advantages of these technologies is mainly it's the high accuracy of measurement. And also they can now do continuous monitoring and provide real-time data, which is very important as well. Main disadvantage, it's very expensive. And also it's difficult to place physical sensors on the tanks. So there are thousands of these tanks around the world, and it is very hard to put sensors on every single tank, obviously. And another disadvantage is that you still need to use assumptions and approximations when interpreting the data. For example, when collecting data from sensors around the tank, you need to account for the wind direction. Otherwise, you may be measuring concentration not just from one specific tank, but from the neighboring tanks as well. And this is where you may use an approximation, or we call it a model. This is where you can use model. So group 2, and that's where we come from, that's estimations, computer modeling software. And main advantage is they're cheap and easy to use. One of the main disadvantages of the modeling software that is currently on the market, and the most common one here is E&P tank software. It's the fact that they don't account for a lot of physical processes that occur inside storage tanks during tank fill up, mixing, pumping, temperature changes, and other processes that happen inside the tanks. These software packages typically use very, I would say, generalized approaches and are based on very simple storage tanks characteristics, such as pressure, temperature, basic geometry, and accuracy of these software models varies between 50 and 80%, which was sufficient, maybe was sufficient 20 years ago, but in today's world, energy regulators are looking for much higher numbers. And this is where our technology is different. So just to summarize the existing technologies, so the most optimal solution in our opinion would be, to solve this problem, would be to bring together the best of both worlds, sensors and modeling. And we've already established that the physical sensing technologies are very sophisticated these days, and it is the modeling component that is still dragging behind. And this is where we can help. So now I want to talk about our technology specifically. So our approach is to create a model and describe all the physical processes that are happening inside the storage tanks. Currently, there is not enough information about what's going on in storage tanks. Typically, it is considered that fluids in cylinders or in tanks are stagnant or simply not moving. In reality, it is constantly moving under the influence of heat from the outside. And this phenomenon is called thermal convection. There are a lot of other factors that are typically overlooked when measuring fugitive methane emissions from the tanks. For example, tank fill ratio, impact of the ambient temperature on the emissions rates, location of the pressure release valves, etc. So based on the information provided by the operator, such as tank geometry, type of product, internal pressure, and many others, we can determine the following valuable data: vaporization rate, methane concentration in vapors, vapor distribution with respect to the radius of the tank, and flow patterns. So one may say, well, that's great information, but then what? So knowing all this information in combination with data collected from the external sensors can help to find ways to better capture or completely avoid fugitive emissions. This data can also be used when designing these tanks. For example, to find the optimal location for pressure release valves or to insulate walls of the tanks appropriately. We have done many years of research and compared our results with the results of other scientists that worked on this problem in the past. And our results proved to be correct. I don't want to bore you to death with all the technical details and formulas. I just want to give you a couple of examples of what our technology is capable of. So on this particular graph, you can see the two graphs in the top left. They show the how liquid is moving inside the tanks or the flow patterns. As you can see in the center of the tank, the fluid is actually moving down, and then near the walls of the tank, the fluid starts to go up. And That's what this proves the fact that there is a constant circulation of fluid on the thermal load from the outside of the tank. And this is actually one of the main causes of methane emissions. The two graphs in the top right corner show the temperature curves in the tank. And this is another very important factor that affects methane emissions from the tanks. This is another example of what our technology is capable of. In this case, we see how fluid is mixed inside the tank using mixers. Our software simulation outputs temperature fields and shows flow patterns inside the tank. To better explain our approach to quantifying methane emissions in the tanks, we need to look at the following example. Typically, these storage tanks are located on so-called tank farms. They can be over 50 storage tanks or on a single tank farm. External sensors measure the total methane concentration at a certain point, but this concentration is mixed with methane coming from other tanks on the farm as well. And vendors usually also install sensors that determine wind direction, and then do an approximation to calculate how much methane is emitted from the specific tank and how much methane is coming from other tanks. And that's where inaccuracy comes from. But they don't know how much methane can be produced by the given tank at certain conditions. We're basically adding this piece of information to complete the puzzle. Our technology was developed by PhD researchers at University of Calgary in collaboration with our academic partner, SAID. In order to do the proof of concept, we're currently looking for industry partners, both oil and gas operators and other technology companies, to run a pilot project on the existing tanks. And also, we're looking for some government funding to continue doing our research. Since I still have a couple minutes for my presentation, I wanted to tell you about other technologies that was developed by Vitas. This is unrelated to methane emissions, but since this is an oceanographic conference, it'll be definitely of interest to some people here. So we have modeled the rupturing effect of liquid films. It turns out that on the thermal load of high intensity, or simply by applying a laser light, liquid films will rupture and form streaks. So what are we going to achieve by breaking liquid films into small areas? This technology can be very useful for oil skimming operations. For example, remediation of disasters like the one that happened in Mexican Gulf in 2010. The area of contamination there was so big that it was easier to break it down into smaller areas for skimming. The two graphs at the top of the slide show how this can be achieved by applying localized light of high intensity, or simply laser light. And then these smaller oil spots can be easily collected by technical personnel. It's another cool technology that we're working on right now, and it can be another topic for the next year's Congress. So I'm gonna stop here. And the end, I want to thank our academic partner, SAID, for their help and support, and specifically Dr. Mertes. And now I will be happy to answer your questions.
Yeah, thank you very much, Alex. Also very interesting addition to the end there. Just, not only what does the tank do, but what happens if the environment has to encounter the liquids. Yep. I don't see any questions in the chats or hands up at this point. I only had one question myself, maybe, because I know that there are some facilities that have what they call floating top storage tanks. Are they part of your calculation as well, or how would they differ?
Yes, absolutely. Yeah. So there are two different types of tank tops. So there is floating roof tanks, and then there is fixed roof. So that's one of the solutions that we can provide to the tank. So we can account for all these different parameters. So for example, with roof, your fill ratio does not change. It'll always be the same because your roof moves up and down depending on how full the tank is. Whereas with fixed roof, your fill ratio will change. So from 0 to 100%. Yeah. So we actually we can model the free surface of the fluid. So yes, this is one of the parameters that we can account for in our calculations and in our models. Yeah. Very interesting topic actually. This actually deserves a separate presentation, to be honest with you. But very good question though. Yeah.
All right, thank you again for your presentation. As I said, if somebody comes up with a question later, please feel free to just put it in the chat so everybody can see it. And with this, we'll move to the next presentation by Paul Lepre. And now we're moving into the work of looking at the uncertainty of quantifying methane emissions.
Yeah, I will share my screen. Just a minute. Okay. Okay, is everyone is able to see the
Looks
slides?
Great.
Okay, perfect. So hello everyone. My name is Paul Lapeyre, and today Daniel Blackmore and I are going to present you our work on a statistical framework for uncertainty estimation when quantifying methane emissions. So Daniel will first introduce the context and our main objectives, and I will then present a simple case study to illustrate the method.
Yeah, so just looking at the background and motivation behind quantifying methane. So the global warming potential of methane is 27 to 30 times higher than carbon dioxide over a 100-year period, and over 80 times higher over a 20-year period. As such, we're seeing more and more regulations aimed at methane emissions reduction, and more technologies being developed to help quantifying methane emissions, such as optical gas imaging cameras, drone-based LiDAR technologies, truck-based technologies, and more. Having said that, reducing methane emissions and enforcing emission regulations requires a level of accuracy of all these technologies. And since these technologies cover such a wide range of types, they produce different raw data and use different models to manipulate their data into an emission rate estimate. There are differing levels of uncertainties across all of these technologies. So the question that we want to answer with our work is how do we quantify the uncertainty of all of these technologies? So looking at some sources of uncertainty, the first source that we look at is the uncertainty of the measurement itself. So this would be things like the sensor accuracy, the equipment being used, even operator expertise. We generally can get information on this from literature with controlled release studies or bench tests of equipment. The next source of uncertainty that we look at is parameter uncertainty. So this is the uncertainty of the parameters that are used in the measurement model. So this would be things like wind data, atmospheric stability, position data, things of that nature. This generally relies on prior information as to the distribution of these measurements. When we get information about this from literature. However, when that's not available, we do a subjective assignment of an upper and lower bounds, and then assume a normal distribution of measurements. It is worth mentioning, however, that we did perform field trials in April across a wide variety of technologies. So we have a lot of data to go through that will help inform us about the parameter measurement distributions. The last source that we look at is the uncertainty of the model itself. So this is looking at the model independently, assuming that the measurements of the parameters and the concentration of methane was 100% accurate. What is the uncertainty induced by using a specific model? To inform us about this, we generally compare these models to more accurate models such as large eddy simulations using the same data sets. So all of this is leading to our objective, which is to use a Bayesian analysis on all of these sources of uncertainty to quantify the overall uncertainty of methane emissions quantification technologies. So the example that we'll be looking at in this presentation is mobile dispersion techniques. These techniques work with truck-based sensors for methane concentration, positional data, wind data, atmospheric conditions, etc. The truck performs drive-by transects of a methane plume and combines measurements across that transect with a dispersion model to obtain an emission rate estimate. The dispersion model that we'll be looking at is the Gaussian plume model. It is the most commonly used dispersion model for mobile techniques. The formula for the Gaussian plume model is seen here. C is the concentration. It's a point concentration that the truck takes with the truck-mounted technology. And QL is the leak rate that we wish to infer. These are linked with a function F, which is a function of parameters such as the downwind and crosswind distance, the source height, wind speed, atmospheric stability class, etc. To infer a leak rate, we do an inversion of F and combine the concentration measurement with measurements of all the parameters to obtain the leak rate. One thing that is important to mention about the Gaussian plume model is that it is a time averaged model, whereas typically we're working with data that is 1 or 2 transects of a plume, which represents fairly instantaneous data. So that induces some of that model error that I was talking about previously.
Okay, so from this formalism, we can identify the different uncertainty sources mentioned before. So first, the concentration will include measurement noise. Second, the model parameters are mostly measured or determined by the user, and this will lead to parameter uncertainty. And finally, the Gaussian plume model is based on a strong hypothesis on the plume dynamics, and this is referred as model error and will add uncertainty to the inferred leak rate. So to account for those uncertainties in the leak rate quantification, we propose using a statistical method that is the Bayesian Inference. And in Bayesian framework, all variables are regarded as random variables that obey probability density functions. So the quantity of interest, the leak rate, QL, the concentration measurements, C, and the nuisance parameters, P, are seen as random variables with probability density functions that are related by Bayes equation. So Bayes equation states the posterior PDF of the leak rate and parameters based on the observed data C. And this information is retrieved from the product of 2 PDFs. So first, the likelihood of observing C, the concentration for hypothetical leak rate and parameters in the context of measurement noise. And second, the prior probability density function of QL and the parameters based on what is known before the measurement. The evidence is there so that the posterior probability density function satisfies the law of total probability. So the PDF of the quantity of interest, that is the probability of QL knowing concentration measurement, is obtained by marginalizing the posterior PDF of Bayes equation over all nuisance parameters. So from this PDF, we can identify the maximum a posteriori estimate and the associated credibility interval. So therefore, through the quantity of interest probability density function, Bayesian framework produces a comprehensive definition of uncertainty. So we studied 2 very basic scenarios to illustrate the method. In the first one, only the velocity is an uncertain parameter and all other parameters are perfectly known. So here is the Bayes equation that we have to solve for the first scenario. And first, let's have a look at how we obtain the likelihood function. So the likelihood probability density function is derived from a measurement model accounting for measurement and model error. So the measurement error is normally distributed and the uncertainty depends mainly on center uncertainty. And model error is also normally distributed and is obtained from a comparison between the Gaussian plume model and a more accurate model. So for example, here we generated the data using a LES CFD simulation. And if we select a slice of the plume, this is how the concentration profile along the red line would look like. And now when time averaging the data, this is how the same slice looks like. And this would be the concentration profile along the same red line. So when comparing the equivalent Gaussian plume model to those profiles, we have an illustration of model error. So after identifying the likelihood function, we focus on the prior information on the velocity. And in that configuration, the velocity was set at 5 meters per second and with an uncertainty of 0.5 meter per second. So combining those two results and marginalizing, then we obtain the quantity of interest PDF with a maximum a posteriori estimate of 17 kilogram per hour and with a credible interval between 6.2 and 26.1 kilogram per hour. So in this example, the LS data was generated with a leak rate of 20 kilogram per hour, so which fits with the results. In the second scenario, only the downwind position is an uncertain parameter. So the downwind position is needed to estimate the dispersion parameters, sigma Z and sigma Y. And in this scenario, the measurement is made at 40 meters away from the stack with an uncertainty of 4 meters. So this will be the prior information that we have in the downwind position. So the posterior probability density function gives an a posteriori estimate of 16 kilogram per hour with a credible interval between 3 and 32.7 kilogram per hour. So, which is a little wider than the previous scenario. So in conclusion, we've seen that methane emission estimates are subject to uncertainty arising from measurement noise, uncertain model parameters and model errors. These effects can be quantified using Bayesian Inference, and this can give a comprehensive assessment of emissions uncertainty. And in the future work, we have to work on this comprehensive assessment of parameter uncertainty and model error, and extend our method to other measurement technologies, which will have produce different raw data, use different models, and with different parameters. So those are some acknowledgements. We thank you for your attention. And if you have any questions.
All right, thank you very much, Paul. We have one question in the chat, which I think is straightforward for you to answer. And it's the question from X. So experience shows that accuracy of methane emission modeling is currently between 50 and 80%. Is that what you see in your calculations as well?
So well, we haven't pushed the method that far because we just used very simple models. So here you can see that I only used velocity and downwind position as uncertain parameters, and each time they were distinct configurations. So there are lots of parameters to take into account at the same time in order to have a realistic estimation of the uncertainty. So from now, I couldn't say from this calculation. Sorry.
All right. See if anybody else has a question, please, put in the chat or raise your hand. I might just ask one myself in the meantime. So for the wind speed, you put, very symmetric error around the 5 meters, the same higher and lower speeds. So if that were the case, if all of those were kind of nicely distributed errors, would you expect to see a significant improvement with multiple transects? I mean, this what you presented is like a one transect uncertainty, is it? Have you investigated what happens if you do 10 transects under different conditions, for example?
Yeah, do you want to answer?
Sure. We are working with a lot of the field trial data that we have from April as well, as I mentioned. So that, again, is going to inform us a lot more about the distribution of these parameters. So this is, again, one of the parameters where we would have just assigned an upper and a lower limit and then assumed a normal distribution. Once we get more in depth into our field trial data, that will give us more information about distributions of parameters such as wind velocity, and that will help make our model more robust and accurate.
All right, let's see, just one more question coming in last second. If you've collected your own data, or do you plan on using data analysis of data already available? Like we've seen some presentations of other people doing these kind of studies. So I'm wondering if you're planning to use some of their data as well.
Well, for now, we are planning to use the data we collected recently. But if that wasn't enough, maybe we could use other data, yes, I guess. Excellent.
Thank you very much for the presentation. Now we're still within time, which is great. So we can move over to Kirk Ossadet's presentation, which will focus on venting issues related to petroleum wells in mostly Alberta, as I understand. Over to Kirk.
Hey, Felix, you can hear me?
Yes.
Okay. Here we are. Which screen do you see? Do you see screen 2?
We currently,
like a full screen?
Now we see the full screen.
Okay, you see full screen. Okay, so my name is Kirk Ossadet. I'll be presenting on behalf of my colleagues Nicholas Udding and Andrew Wigston, who were with Natural Resources Canada CanMet, and my colleague Don Lawton, who is the director of our institute and retired professor or university professor at the University of Calgary. Topic today are well integrity issues, and there are several types of well integrity issues. These include surface casing vents and gas migration, as well as aquifer contamination, which will be the focus of our discussion today quite briefly. There are other types of issues such as casing failures and abandonment failures, which were addressed in some of the other talks this morning. But basically, surface casing is where it was a safety device to solve the problem of sustained casing pressure. It's a pipe that comes out of the surface casing. Gas migration occurs outside the annulus of surface casing, and the gas comes to the surface. Just as a comparison, there's a lot of discussion about the upstream petroleum industry emissions from wells. But at our Newell County Field Research Station, we have 9 wells. 3 of them are AER wells. The other 6 are Alberta Environment and Parks water wells. So there are quite rigorous requirements for wells drilled under the authority of the energy regulator. They have to be tested shortly after construction. There's mandatory reporting if they fail that test for a period of 5 years. And either the well is remediated immediately, depending on the characteristics of the surface casing vent or any gas migration, or the well then is remediated at the time of abandonment. There are about 542,000 subject wells in the Western Canada Sedimentary Basin. And wells at our site are typical of many, or actually almost most of wells, in that they emit less than 1 cubic meter today. In contrast, the bottom here with Nick Udding, we see one of our water wells, and the sandstone aquifers in Alberta are commonly low permeability, and many water wells are completed in coal zones. So essentially, water wells are like coal bed methane wells in much of Alberta. Our domestic well emits 40 cubes per day when we begin to pump, and this increases as we lower the head. The well often volunteers gas even if it's not pumped, as do other water wells that we have. There are about 250,000 of these wells in Alberta, and of course, there are very minimal requirements for their testing, monitoring, or remediation. Well integrity issues are unpredictable, and there are diverse causes. They affect about 6.6% of all wells, all AER wells in Alberta. This is typically a function of well construction, such that factors like who constructed the well is important, because human failures are more important than material failures. the age and requirements of regulations at the time that the well was constructed, and how it was designed. How the well's prepared for cementing is very important, and the actual details of the cementing program. As you can see, if you simply cement to surface, you can reduce the well integrity emissions by about threefold. Of the leaks, about 25% of the leaks come from the producing zone, while 75% originate in shallower strata and migrate through the cement-filled annulus to the surface casing. The typical migration of the surface casing is in part because of the larger diameter and also because it connects to the atmosphere at lower pressure. We do know that wells that are well constructed, and by using the model of acid gas disposal wells, these wells that are well constructed for purpose tend to have fewer integrity issues than wells that have been converted from other purposes. And this leads some people to say that drilling engineers should always spend time in the abandonment department before they go on to drilling new wells. Okay, so here's what it looks like. There are about 10,000 wells as of 2016. The wells are classified into serious wells and non-serious, where the non-serious proliferate. And the number of wells with surface casing vent flow continue to grow, while the number of wells with surface casing vent flow or gas migration is declining. There is, however, a lack of abandonments. And so abandoning inactive wells with surface casing vents could be an effective but costly strategy to reduce the number of wells emitting, probably about a third of the total emissions that would come from these two sources. If we actually look at the amount that's emitted, it's about 1.17 megatons of CO2 equivalent, and this is very comparable to the CO2 that's managed by the Shell Quest project on an annual basis. Well integrity emissions account for about 20% of Alberta's upstream petroleum industry methane emissions. And the total annual emissions have been decreasing since about 2008, largely because we have fewer and fewer serious wells. This would include wells with gas migration. So the average non-serious well emits at 13 cubic meters per day and strongly skewed, with most of them emitting less than 3 cubic meters per day. Amongst the serious wells, it's similarly skewed with an average emission rate of about 310 cubic meters per day. The impacts are noticeable. Obviously, there are safety impacts because it's a dangerous good. Typically, the safety impacts are more commonly associated with distributions and pipelines in the various parts of the petroleum value chain. The exception to that might be Wheatley, Ontario, where a very old abandoned gas well might have had a structure constructed over top of that. That would be a regulatory failure. So what we recognize are safety risks are greatest where wells and pipeline infrastructure are older. And this, particularly with respect to pipelines, this reflects the use of cast iron gas mains. Safety can be solved simply by proper setbacks, zoning, and regulatory surveillance. As I mentioned, leaks from pipelines are not just an upstream issue, but they're also a midstream and downstream issue. Just like the bicycle that they ride around Toronto, there have been several studies in a number of cities. Boston was one of the first ones where they found 3,365 leaks along 785 miles of streets, some with up to 15 times background. And this was largely brought on by recognizing the impacts of gas leaks on vegetation, which we'll talk about next. Carbon isotopes confirmed this almost all gas, and the leak frequency was linearly related to the number of miles of cast iron gas mains in Boston. Very similar results have been reported in Washington and other European cities, and today we heard about a somewhat similar report from Toronto. Plant impacts have been known for a long time, so these would affect both pipeline leaks and gas migration at well sites. Higgs was the first one to determine that the primary cause of pathology was plant asphyxia because of the oxidation of methane by anaerobic methanotrophs in the soil. Chemical toxicity, I'll discuss in a minute, but it can occur. Species toleration varies considerably as many plants actually show a slightly beneficial impact. You can see here the dead zone of asphyxia. You can see an area, this is actually a natural seepage, an area where there's green vegetation enhanced by the seepage, and then the background that goes farther away from that. Methane itself is a common and non-toxic component of groundwater and sediments and sedimentary rocks. There's no pathology associated with methane, and many farms in both southwestern Ontario and Alberta, Saskatchewan, British Columbia have methane separators. And of course, methane is sometimes a natural product in our own gut. Gas migration represents a very small number of wells, and it is required to be remediated. So I'm not really worried about what the flux would be from gas migration as long as the remediation continues. Aquifer contamination, that's typically a deeper aquifer contaminated a larger distance away from the well. The Kelly report of a blowout in Ohio is the exception that proves the rule. In Western Canada sedimentary basin, there are about 12 documented cases, not all of them ironclad, of aquifer contamination by petroleum wells. So aquifer contamination is essentially a very small risk. What does happen with gas migration, of course, is acidification of groundwater, and this can result in both phytotoxic effects and bioattenuation, as we saw, very similar to what happens with the pipeline leaks. Climate impacts go without saying. They've been mentioned by a number of people before, and the reason why these emissions are being addressed now is to reduce their climate impacts. So to conclude, well integrity issues have and can be addressed by performance-oriented regulations, improved planning, and well construction. Material failures are rare, but human failures in the application materials remain an issue. Abandonment with vented caps of the many inactive wells is an effective but costly strategy for reducing non-serious surface casing vent flows to the atmosphere. And regulations for methane emissions currently require abatement on site. But perhaps a greater methane emission reduction could be achieved by some type of offset where managed agricultural or other emissions could be more beneficially and economically reduced to achieve greater climate goals, because the atmosphere doesn't care where the methane comes from. Okay, thank you.
Thank you very much, Kirk. There's already a question for you from James Williams about what happened during recent years in the pandemic. Did you see any significant changes in the number of abandonments? It's not related to the pandemic. It's related to the provision of federal money to assist with the abandonment of orphan wells. So there's actually a prioritized list. Those companies who are still operating carry the wells as a liability on their balance sheets, and this actually affects this sort of environmental performance. Actually, affects their credit rating and their share valuation. Where companies have actually gone out of business and have not remediated the wells, there is a separate fund that is paid into by all of the operators called the Orphan Well Fund, and now it's augmented by a federal bolus of money, which is being used to address those funds which have become the responsibility of essentially the Orphan Well Association,
which is really the province, and to reduce the emissions from these particular wells. And a number of them are fairly serious and persistent emitters.
Excellent. There's one more question I think we have time for from, I think, Khalil Ahem. In terms of mitigation of gas migration emissions, does the process involve well repair, or can repairs be done by enhancing the soil's capacity to oxidize the methane?
Currently, it's looked upon as a well integrity issue, and so it must be repaired, primarily by reperforating the metal casing and rubberizing the existing cement and reinducing cement at high pressure to seal the well. Currently, although there have been some discussions about bioremediation, it's not an acceptable process with the regulator.
All right, thank you very much. Don't see.
I guess I should just mention that's primarily because we don't have a quantitative universal model for minimizing the effects on plants and crops, which is where most of these wells are situated. I mean, if we could control it, so it actually became a mechanism for enhanced plant growth, then it would actually become a desirable feature, but that's certainly not the case yet.
Excellent. All right. Thank you very much. So now we had 3 general talks. Now we have a little short teaser presentations for 2 more posters that you might have seen or might have not seen. So we'll have Martin Lavoie talk about the first poster, and then afterwards Gilles Perrin will talk about the second. So we'll start with Martin, please.
Can you see it, Felix?
Yep, I can see the slides.
Okay, thank you for the opportunity. My poster is about a paper we recently published in Cleaner Environmental System. It's about ESG reporting, and ESG stands for environmental, social, and governance. So ESG reporting is still not mandatory in Canada, but there are more companies now publishing ESG or sustainability report, and same goes for oil and gas producer. Why? Well, we know that there's in general a link between ESG reporting and financial return. Earlier today, we heard about that methane emissions were underestimated. And last year, our lab published a paper showing that methane emissions were underestimated by 1.5. So we got curious and we wanted to know if underreporting of methane emissions by the producer was also existing. So the question was, how does self-reporting compare to methane inventories? And we concentrate on Alberta because, well, first it's the largest producer, but also data was, it was easier to get access to. So we used 4 different ways to calculate methane emissions. First was by the information submitted to the regulator, which is AER in Alberta. Also based on the inventory done by ECC, Environmental Climate Change Canada. The third one was based on the inventory the Flux Lab did, and it was published last year. And finally, the last one was self-published value in ESG reports. So just a couple of graphics. I don't know if you see, well, the graphic, but on the x-axis, you have the methane emissions per oil and gas produced. And on the y, it's the producers. So overall, I mean, 2 main points is, as expected, methane intensity was much lower with the data submitted to the regulator than the inventory from the ECC and the Flux Lab. And it was, in average, 18 times lower in Petronex than with the Flux Lab inventory. And the last graphic I want to show is, I think it really summarized very well the results of the paper, is just first of all, we started with 70 producers. We went through all the website, and only 50% of the producer had a sustainability report, and only 30% of them had methane intensity in their report. And overall, as you can see, that the distribution of the methane intensity in Petronet is really narrow. And as we should expect, the distribution with the ECC and the flux lab inventory is much wider. And you see that there are some larger emitters in the group. So in summary, it's just regulatory submissions capture only a small amount of the total methane inventory. And we also observe a low bias in regulatory reporting. Thanks.
Thank you, Martin. And now we have a 5-minute quick presentation about the poster from Gilles. I hope.
Hello.
Oh, there we are.
Hi. Can everybody see my presentation?
Yes.
Awesome.
No, just switch away.
Oops.
There we are.
There we go. So, hello everybody. I'm Gilles Perrin, and I will be presenting basically a study that's ongoing currently, and I'm at the stage where I'm able to have a preliminary set of results. And I'm basically looking into methane emission from inactive oil and gas infrastructure across Western Canada. So by inactive, I'm especially digging into suspended and abandoned wells across Western Canada, and abandoned as described in the Directive 020 as cut and capped wells, and suspended described as oil and gas well that has not been producing for more than 6 months. So it is very somewhat, actually, it is very well understood that, oh, it's not, sorry. It's not moving. Oh. Awesome. So fugitive and venting emission from the oil and gas industry across Western Canada is being very well quantified and better understood as the years goes by. However, it is not as, however, inactive oil and gas emission is not as well understood as emission from active infrastructures. And that's basically where the focus of my study wants to be. A lot of the studies that we've done in the past oftentimes focus on active and suspended wells specifically, and did not put a shining light on the whole picture, while including abandoned wells also. So a large part of my study involves mining for basically a lot of the data that we already have, and add back a lot of the abandoned wells into our main source file, and reprocess a lot of the data to be able to get a clear picture of what would be inactive, what would be the spread of inactive oil and gas emission across Western Canada. This work is, so before going into the preliminary result, the survey area that I've collected data from, so all the aggregated data that have been collected basically are from all 3 provinces, BC, Saskatchewan, and Alberta. The main sites really are Lloydminster, Peace River, Grand Prairie, Fort McMurray in BC, Whitecap. There is also Kindersley, and some other big oil and gas producing centers, I'd say. And from all of those studies, basically, I've compiled all of them, extracted all of them, and during the reprocessing process, so in a nutshell, the reprocessing process involve grouping all the oil and gas infrastructures into a radius of 45 meters, and then attribute a point measurement done with the truck outfitted with a cavity ring down spectrometer in the form of a Picaro, which is the actual brand of it. And And then that measurement is basically put into a back trajectory analysis, which is then and after that, the volume is then estimated, the volumetric estimate is then basically output using a Gaussian dispersion model. Sorry, there's a lot to unfold there, so I'm trying to go as fast as possible. So once we're able to compile all the volumetric estimate, that basically perform an isolation analysis, because it is very hard to pinpoint emission from inactive oil and gas infrastructure, so wells. My way of doing it would be to really look for isolated wells, and isolated in a sense where they are within 1,000 meters, so 1 kilometer away from the nearest infrastructure, and knowing that on a map there is no other possible source of methane. So, while after that analysis, after that isolation analysis, those are the preliminary results. So on the left side, you can basically see a count of all the regions that have known emitting inactive sites. The greatest amount of them is Lloydminster. There's a specific reason for that. It's because Lloydminster is one of those regions that we actually sample, where we actually perform campaigns there more than 2 times. Actually, it was 3 times. I used 3 different years of surveys for Lloydminster only. So it would be logical that Lloydminster would have a higher count, not maybe because they have a larger amount of emitting inactive infrastructures.
Thank you very much. I think just maybe if you have a final statement, I think I can definitely recommend everybody to go and get much more detail as well at the poster.
Yeah, of course. Inactive oil and gas well actually do not emit as frequently as active infrastructure, but when they do emit, they emit just as much as active infrastructure. So it's very important to actually understand them better. And we are in the process of actually doing a possible field study to understand them better, because we lack actual focus, good measurement on those in this area.
Thank you very much. I think it's an excellent tease for everybody to join you as soon as possible, once we're over with our session, to come to visit you at the poster.
Thank you.
Looking at the time, we'll have to move on to the next presentation, and we'll be moving away from Western Canada further to the east now, with Khalil El-Hajem, presenting work on oil and gas wells, not in the Western Canadian Central Basin, but in Ontario.
Okay, so I'm sharing my screen, but for some reason, the slideshow is not starting.
Yeah, we can just see the regulars there.
Okay, I can do it this way if it works.
You can try at the bottom, maybe if the presentation doesn't work, you just maybe go to read mode. It's the second best option typically.
Thing is, okay, I'll just stop sharing and share again, because it seems the mouse is not working. So I'm sorry, where's the read mode?
You go to the bottom where you typically have this presentation symbol. The run next to it is the read symbol. So very bottom right where you do the change the slide size.
Yeah, my mouse is not pressing for some reason. So like not even the slide is not changing when I press on the keyboard. So that's odd. Sorry, I'll just give it another shot. I don't know. So I'm not sure what can I do here? Okay. Can I just have a minute? I'm sorry.
I mean, you could try putting, like if you started, just press F5.
Okay, let's see.
See if the mouse doesn't work, maybe your keyboard helps.
Felix, if not, I'm fine with presenting now. Maybe give Khalil some time to figure it out. If that's an option, I don't know.
No, just try to see if F5 would work for now.
It's not working as well.
Oh.
Yeah, I'm not sure what's going on.
On our end, it seems the mouse is moving, but maybe not really.
Yeah, so basically the mouse is working when I'm in Zoom, like share screen, it's obviously working. But once I start sharing, it seems that it's not working in PowerPoint for some reason. I'll try to close PowerPoint and start it again.
All right, last try then. Otherwise, we'll have to maybe move people around. It's not ideal moving people around if somebody's joining late or early, but if James is willing to go early, we'll take that offer.
Give it a shot now. Okay, now I think it works. No. Okay, yeah. Okay, so today I'll be talking. Okay, so today I'll be talking about methane and hydrogen sulfide emissions from oil and gas wells in Ontario. So to start, an oil and gas well is a subsurface structure that is designed to extract petroleum hydrocarbons from hydrocarbon-bearing formations all the way to the surface. And it intersects different subsurface formations, and in some cases, including groundwater aquifers. So it can act as a leakage pathway for hydrocarbon formation fluids to reach groundwater aquifers and the surface as well. So in this work, we focus on 4 types of wells. The first 2 types of wells are producing wells. The first type of producing wells are marginal wells, and these are low producing wells that produce 1,700 meter cube of natural gas per day or 1.6 meter cube of oil per day or less. And active wells produce more than 1,700 meter cube of natural gas per day and more than 1.6 meter cube of oil per day. The other category of wells are abandoned wells, which also includes suspended wells. And these are wells that are plugged or unplugged, but do not produce hydrocarbons. So we focus on Ontario because oil and gas exploration in Ontario started in 1858, and it led to an oil rush. It's estimated that in this period, in the 1860s and 1870s, around 50,000 wells were drilled. Of these wells, it's estimated that 30,000 wells are undocumented. So also because these wells were drilled like in the 1860s, they are really old, and many of them were plugged before the implementation of modern plugging standards. So here on this slide, we see a picture of a technically plugged well, but it's really not plugged because it was plugged ineffectively, and emissions and water leakage from this well led to the formation of this pond. So we focus on 2 gases. Methane, as we know, is a very potent greenhouse gas. Also, methane emissions from abandoned wells specifically are very uncertain in Canada's National Inventory report. So it's really important to collect more measurements from this well category to get a better idea of the true emissions. Also, measurements of methane emissions from all types of oil and gas wells were not available in Ontario prior to this study. We also focus on H2S emissions because H2S is a highly toxic gas that is damaging to the humans, animals, and the natural environment. H2S emissions from oil and gas wells are not accounted for in Canada's air pollutant inventory, and that is because there's no available data on H2S emissions from oil and gas wells. So in terms of the measurement method that we use a static chamber methodology. So what we do is we build the chamber to enclose all above ground well infrastructure, and then we measure the concentration of gases inside the chamber for a specific duration of time. In this project, it was for 15 minutes. And then we fit a linear model to these concentration readings. The slope of the linear model represents the change in concentration over time. Then we multiply that by the volume of the chamber, and we get an emission rate in mass per time. So in our results, we found that high methane emitting abandoned, marginal, and active wells all emit in the same order of magnitude. We also found that on average, wells emitting H2S are the highest methane emitters. Here, I just want to note that we found positive H2S emissions at 3 wells only, but all these wells had very high methane emissions. So our preliminary result is that H2S emitting wells are high methane emitters. We also compared our emission factors for plugged, abandoned, and producing wells in Ontario, and compared them to to methane emission estimates and Canada's greenhouse gas inventory. And we found that plugged abandoned wells in Ontario are underestimated by a factor of 920, and producing wells, which includes active and marginal, are underestimated by a factor of 2.1. In terms of hydrogen sulfide emission rates, as I said, we were only able to find positive emissions at 3 spots. These spots, one of them is an abandoned unplugged well. The second spot is an abandoned plugged well, but this is the abandoned plugged well that I showed initially. So this is the abandoned plugged well. So it's technically not plugged. And the third spot is a wetland area. And in this wetland area, we attributed the emissions to a potentially undocumented well, because in this wetland, we did multiple measurements across the wetland, and we only found emissions at a very specific spot. We also studied the carbon isotopes of the methane that we got in this wetland, and we found that the methane is really heavy, which means that it's coming from an oil and gas source. We also studied the attributes that affect methane emission rates, because this is important to know which attributes affect the emission rates in order to concentrate mitigation efforts when we're trying to reduce these emissions. So we found that plugged wells emit much less methane compared to unplugged wells. We also found that the well status, active, marginal, and abandoned, plugged or unplugged, affects the methane emission rates. And this highlights the importance of collecting measurements from all types of oil and gas wells to get a better picture of what these emissions look like. We also found that wells plugged before 1997 emit much more methane than wells plugged after 1997. And we chose 1997 as a cutoff because in this year, the Oil, Gas, and Salts Resources Act in Ontario became a law. In terms of our insights and recommendations for future studies, maybe. So the number of H2S emitting wells in Ontario and elsewhere in Canada or in the United States requires further study. Because we found H2S emissions at only 3 wells, but the potential occurrence of H2S at other oil and gas wells in Canada may mean that that oil and gas wells are a significant source of H2S emissions. It's also important to conduct additional measurements from H2S emitting wells to understand the relationship between H2S emissions and methane emissions, because as I said, the H2S emitting wells that we found were very high methane emitters. So this may affect greenhouse gas inventories. Also, although undocumented wells are most likely emitting methane and other gases, they are not accounted for in inventory well counts. And records for these wells do not exist. Like, we just know that they are there. We don't know any of their attributes. We don't know what they produce. So it's really important to measure these wells and know how much of these wells we have. And that's it for me. Feel free to ask any questions. Thanks.
Thank you very much, Khalil. Let's see, I don't see any questions typing in the chat yet. If anybody has a question, you can also raise your hand as one of the Zoom activities. Don't see anything yet. So one question I would have is that you mentioned that there are about 30,000, or you said 50,000 were drilled in the early days. And about 30,000 of those are undocumented. Do you have an idea how many you would have to sample to get a good estimate of what the overall emissions are? Because obviously, you know, sampling a few hundred might not be enough to get an overall idea about how many emit a lot and how many emit a little.
So in terms of undocumented wells, so we've only measured 1 in Ontario. And as you said, we need many measurements. I'm not sure if I can provide an exact number of how many wells we need to measure, but like maybe we can measure as many wells as other wells have been measured. Like once we're confident enough in the emission factor that we're computing, then these measurements should be considered enough, but I cannot provide a value.
Okay. There's a question now. Sarah, the well picture in your slide, you mentioned that this was plugged, but technically unplugged. Oh, so now it suddenly moved. To just move back to the question. Somehow the chat moved on my end, sorry. I'll finish the question. Is it representative of other plugged, unplugged wells for whichever category it fell under?
So it was counted in this study as plugged because it represents the conditions of other plugged wells in the region. So we didn't want to say it's unplugged because in the library, it's stated as plugged. So when someone's going to estimate these emissions for these wells, they're going to say that this well is plugged. Like they are not going to go to the field and check that it's technically unplugged. So that's why we considered it this way.
Thank you very much. It's still a worrying sight to see a plugged well, quote unquote, looking like that.
Yeah, and actually this picture doesn't show really the environmental impacts of this well, but because the flow from this pond is going to the opposite direction, but it's really devastating to the vegetation, to the trees. Like we see the rotten tree trunks. It's quite an.
I think we have time for a quick question from Kirkstall.
Oh, actually, it's a bit of a comment. In Ontario, most of the mineral and petroleum rights are held by individuals, and so those individuals were effectively partners in those wells. So, is there any effort to even if the corporate entities, like many corporate entities, will still exist to some degree, like Imperial Oil, but is there any effort on the part of the regulator to track down particularly the mineral rights owners and require them to remediate particularly the H2S emitting wells?
Mm-hmm. So basically, for the H2S emitting wells in Ontario, as you said, the situation is a bit complicated because many wells are like owned by the actual landowners. So I know that there's been some interest in remediating these wells, but I've been visiting them since 2020 and the situation has only gotten worse. Like I know that the operators or the people who own the land where these wells are located are very annoyed with how this problem is being handled. I know that there are some initiatives such as the well abandonment programs, which allows for people with wells in their backyards to apply for funding to plug these wells. And I know also that they were giving priority to the wells that were emitting H2S, but so far they haven't plugged neither of these wells.
Well, as you say, it's getting worse every year, the longer we wait to remediate the wells, right?
Absolutely.
It goes to show the historical aspects of this problem.
Yeah.
Yeah, I think it's a really good point to raise it and, you know, have such a very striking image as well to underline the seriousness. All right, thank you very much. We'll stick with the topic of abandoned wells in the next presentation by Geneviève Borloo.
Right, hi. Can you hear me?
Yes, we can hear you.
And do you see the presentation mode?
Now we see the presentation mode as well.
All right. Sorry. So today I'll be talking about something maybe a little bit different, but that actually relates a lot to what Kirk also has been talking with the leaks in groundwater. So I'm going to be talking about, well, do underground leaks from abandoned oil and gas wells that go through shallow aquifers significantly contribute to methane emissions? And if so, how can we detect them? So first, I'll just talk about two studies just to put things in context. So the first one is by Williams, which showed that, yeah, in Canada, there's approximately an estimation of 373,000 abandoned oil and gas wells, which are mostly located in Alberta and Saskatchewan, as the map shows there with the orange dots. And in terms of emissions, like we have heard before, globally open wells were found to emit more methane than plugged wells, but among the plugged wells, those that are vented were found to emit just as much as unplugged wells. So that obviously shows the effectiveness of flooding the wells in terms of reducing atmospheric emissions. So that's on the one side. And then on the other side, if we look at another study by Dussault and Jackson in 2014, they have shown that, well, the wells in Canada are often vented, while in the USA, it's more common that they are completely plugged, not vented. They also said that, according to them, the most serious concerns are latent and long-term in consequence and are due to the shrinking, cracking, and aging of the cements. And they found that the most likely mechanisms, because at that time people were there were a lot of concerns related to fracking, but they found that the most likely mechanisms of environmental impacts from fluids were twofold. So one was surface casing vent flow, as we have heard. So the gas would escape either from the annulus between the production casing and tubing, and or between the outer cement and the bedrock wall in what they call a micro annulus that might form there. They also said that in general, in Canada, the gas that escapes from the top of the well shows an isotopic fingerprint that is related to mostly the intermediate zone. So like we have heard earlier today, mostly above the targeted zone, but below the aquifer, so from that intermediate zone, and relatively uniform. So that's one mechanism. And then the second is gas migration to shallow groundwater. So it can actually escape directly at the top of the well, but it can also escape in the groundwater if it migrates between the outer cement again and the bedrock wall. And this upward gas migration into shallow aquifers will usually occur as pulsed flow. So the gas will accumulate until it reaches a certain pressure above which it's going to go up as a slug of gas rather than continuous flow. And if we are in a confined aquifer, then this upward migrating gas will encounter an aquitard, so an impermeable or relatively impermeable layer, and then it will start migrating laterally. So lateral transport could be significant in those cases. And if we are in presence of an unconfined aquifer, then the gases that escape to this aquifer will eventually reach the atmosphere. So either through existing groundwater wells, like we have seen in Alberta, or it could simply diffuse through the unsaturated zone. So obviously that needs to be taken into account into total emissions. So we have those two scenarios here. The first one, surface casing vent flow, it's point source leak, quite usually uniform isotopic composition. So it's more straightforward to link a leak to a well. And then in the second scenario, it's a non-point source leak, and it can also be blurred by the likely presence of natural methane in the aquifer, which might make it difficult to actually distinguish natural methane from a leak from an oil and gas well. So I'll just show today like a rapid, timeline of the work that has been done, because I don't come from the atmospheric emission disciplines. I do most of my work on groundwater. So in the groundwater community, what has happened over the last decade, well, as we know, there's been rapid development of unconventional techniques for exploiting oil and gas, which was accompanied by public concerns and moratoria that were put in place in different jurisdictions. And so that gave rise to research. So there's been several groundwater studies in the US, in Canada, and in other countries. And among them, we have three major multidisciplinary studies that were done by the Geological Survey of Canada. And that's what I'm going to be talking about today. I'll be showing you briefly the findings from those GSC projects that pertain to assessment of shallow groundwater vulnerability to deep activities. But also we developed a method for source apportionment of methane, so either thermogenic or microbial in aquifers. And finally, I'll just show you what it means to me for the future in terms of assessing the risk and how to detect leaks from aquifers. So I just forgot to show you. So those are the three regions where we did the projects. There's one in Quebec in the St. Lawrence Lowlands, one in New Brunswick in the Sussex area, and one in Fox Creek, Alberta that is still ongoing, this third one. So those two projects were a good partnership actually between the government, academia, and the private sector. So the oil and gas operators on the sites have shared their data with us, and they have allowed us to drill monitoring wells right next to their oil and gas wells. And the projects were multidisciplinary. They included hydrogeology, hydrogeochemistry, structural geology, geophysics, geomechanics, and I was responsible for the hydrogeochemistry component. So that's what I'll be talking about. And so in this component, what I did was repeated sampling over time of the same residential and also shallow monitoring wells. So we had those two classes of wells. And we analyzed samples for concentrations of major ions, alkanes, so methane, ethane, propane, dissolved in organic carbon, and a lot more. And we also monitored the isotopic composition of methane, DIC, and the water molecule. And we estimated groundwater residence time using tracers like tritium, carbon-14, and chlorine-36. And so what I wanted to do with the hydrogeochemistry component was to assess potential contamination, obviously, but also to develop a framework for methane source apportionment. So I'll be showing you three main findings from the hydrogeochemical aspect. So this graph here is a summary of the wells from all of the three projects. So we see the number of wells as a function of methane, mean methane concentration in this well. So we see that in the three regions, most of the wells had no methane or very little methane, but still there's a bunch of wells that had variable methane concentrations, so up to above 40 milligrams per liter. And that is really high in groundwater because it's actually above the solubility limit of methane at atmospheric pressure. We also noted that in a given well, concentrations varied significantly over time, especially in wells with high methane concentrations. But we also found out that much of this variation was induced by the mere fact of lifting the sample to the surface, which caused degassing, even if we were careful. And so that means that measuring concentrations is not really reliable if we want to find a leak. Second finding is related to the isotopes. So here you see a violent plot of the carbon delta C13 of methane, and for given wells for which we had lots of data. And the color represents the methane concentration. So what we see is that for a given well, there's a lot of variations in the isotopes for wells that have low methane concentrations, but that makes it very difficult to interpret the origin of the methane. And then if we look at the methane, the wells with high methane concentration, so the darker orange, we see that they have very little, well, comparatively little isotopic variation, so which is good for interpretation. However, if we look at what it means in terms of origin of the methane, so thermogenic gas would look like this, microbial gas looks like this. And so you see that there's a band of overlap between the two origins, and that's where most of our interesting wells tend to fall. So it means that it can be tricky to interpret the origin. That brings me to my last finding that I want to show. So it's related to the processes that affect methane. Here we have a typical Bernard diagram that shows the carbon isotopic values of methane and the dryness ratio, which is methane over ethane plus propane. And we have the general fields there with, like in blue, we have microbial gas, in pink, we have thermogenic gas. And you see that among all of our samples, a lot of them fall in this sort of blurred area that could represent a little bit of everything. So we use different strategies with the geochemistry and the isotopes to study different processes like mixing between thermogenic and microbial gas, oxidation of microbial gas that may make it look like thermogenic gas, late stage methanogenesis, which is microbial methane being produced on an old reservoir of carbon that is sort of depleted. So isotopically, it changes the values. And then secondary methanogenesis, which is microbial gas being produced from substrates that used to be thermogenic hydrocarbons that have been degraded, and then they're used by the methanogens to produce different methane. And so we used a wide suite of isotopes and other parameters, and that allowed us, by following a methodological approach, to attribute these different processes to the different wells and to understand what was going on and to understand where we had thermogenic gas or not. And so that shows that the knowledge and a good understanding of the sometimes very complex baseline methane dynamics, so all natural methane dynamics, is necessary in order to be able to detect an eventual leak from an oil and gas well. And most importantly, actually in our 3 study regions, we found no evidence of contamination of groundwater by the oil and gas activities, which is quite a good news. And so what that means for the future, well, there's 2 components to this. So the first one is in terms of risks. So as I said, in Canada, the common practice of surface venting may have caused maybe more leaks to the atmosphere, but at the same time, it has reduced the risk of groundwater contamination. And eventual plugging of the wells, like for example, as you may know, the province of Quebec has decided to decommission all oil and gas wells and to ban those activities in the future. I don't know if they're going to be plugging them completely or not, but if so, that may increase the risk of groundwater contamination. And also in all cases, the aging of the steel and the cement in abandoned wells will also increase this risk. And if there are leaks into fresh aquifers, well, that causes problems for groundwater quality, lowering the pH, increasing metal concentrations, but eventually this gas will also go towards the atmosphere. And finally, what can we do to monitor? Well, as I showed, discerning a leak from methane from an oil gas well compared to naturally occurring methane in aquifer is not a straightforward task, and that will probably show also in the emissions from these aquifers. So we need a good understanding of baseline conditions, and we need to implement really good, like really strong monitoring programs for that. And what we could actually do if we want to detect a leak is to monitor for either a sudden or a gradual but marked change in either concentrations of methane or the acidic values. And what could be also interesting in the future is to put probes, downhole probes, like in monitoring well, that would monitor continuously and communicate the data in real time so that we could react quickly if we see there's an increase in concentration. We can sample and see if the acidic values have changed. That's it. Thank you.
Thank you very much, Genevieve. Interesting to go at the problem from a different direction, quote unquote, in a different liquid. I'll keep an eye out if there are any questions or raised hand. I was wondering, we heard a presentation earlier today by Regina Gonzalez about using radiocarbon in methane as a proxy to look at the origin of the methane that you see. Would that be something you've been contemplating to use for the dissolved methane as well?
We have done that. And we found that all of the methane, we have done that in one of the projects, so the one in Quebec, and we found that all of the methane was really old in this area. And what's interesting is that we had lots of thermogenic methane in the shallow groundwater because the geology in place, like it used to be buried under like over a kilometer, I think, of sediments that has eroded since then. So the conditions were in place for the formation of thermogenic gas, and the rock is so impermeable that the gas is still trapped there. And so when we drill a well, it starts to degas in the well. So we have this thermogenic gas, and we also have microbial gas, and we checked for the radiocarbon in the methane, and it was all really, really old because even the microbial gas in this really tight rock formation has been produced probably a long time ago, or at least from old substrates. So it was interesting, but it didn't like change our interpretation of the site.
All right, great. Thank you very much. Again, if somebody else comes up with a question, please put it in the chat. We can look at it later. Thanks again. With this, we go to the last presentation for the current session by Philip James Williams. And I think he's going to talk about a bit more than just natural gas. Towards the end of the session, maybe something that includes a few more elements before we go into the break. So over to you, James.
Thanks, Felix. You guys can hear me and see my screen?
Yep, that works
perfect.
Well.
Okay, great. Yeah, so hello, everyone. My name is James Williams. I'm a PhD candidate at McGill University, working with Professor Mary Kang. And yeah, as Felix said, today I'm going to be presenting something a little bit different than what we saw from the first two sessions today. Mainly, we're looking at urban methane emissions, specifically from Montreal, Canada. And this work we did in partnership, of course, with Environment and Climate Change Canada, so with Felix and Sebastian. So really quickly for an introduction, so cities are responsible for about 20% of methane emissions globally, and that number or that percentage increases when we look at North America. So that number going up to 36%. And cities are really interesting, and they're kind of fun to go and measure because they're really challenging. There's a lot of these co-located methane sources. So they really pose, in some cases, these unique challenges for attribution and monitoring and measurement. And of course, these are all like critical components for developing greenhouse gas inventories, which will in turn inform where mitigation efforts should be focused. And when we're looking at North America, usually we're really focusing on the waste sector and natural gas distribution when we're talking about the major contributors of methane emissions. And what I'm going to be presenting today are basically individual source measurements, specifically static chamber measurements. And I'm going to show how they can provide the level of detail necessary kind of to improve municipal greenhouse gas inventories, maybe identify some new sources that weren't considered before. And ultimately, the goal is, of course, to reduce methane emissions. So for the scope of work, I think my title of my presentation is a bit misleading because I talk about mitigation and differentiation, but I'm just not going to have time to get into that. So I'm really going to focus more on the quantification side of things. But I do have slides if anyone has questions about mitigation or the geochemical component. But really, I'll be looking at detailed individual source measurements for 3 sources. These are natural gas distribution, historic landfills. These are landfills that were closed basically prior to the introduction of the Canadian Environmental Protection Act. So these are old landfills, some almost 100 years old. We're also going to be looking at manholes. And you can kind of see snapshots of these different sources. On the bottom here, we actually have a chamber around a natural gas distribution station. In the middle here, just a picture of a manhole that I'm sure everyone has seen before. And at the top here, we actually have a chamber over a observation well that's stationed on a historic landfill in Montreal. Then what I'm going to do is we're going to look at these methane sources and compare them to Montreal's greenhouse gas inventory. And this will be important also because 2 of these sources that we're looking at, namely manholes and historic landfills, these aren't included in Montreal's greenhouse gas inventory or any greenhouse gas inventory. So these are kind of these new sources that we're looking at. And we'll see how they compare to other methane emission sources. In terms of the methods, well, we performed a total of 619 static chamber measurements. If you might remember, the static chamber method is the same method that was used by Khalil, who presented a few presentations ago. And I think he did a good job in explaining it, so I'll kind of keep this to a minimum. But we used a static chamber methodology hooked up to either a Sensit portable methane detector on the top there or a Picaro gas scouter, which you see at the bottom. Both have their own strengths and weaknesses. The good thing about the Sensit at the top is that we can go all the way up to 100% methane, which is great for those high emitting sources, but it's not super great at like anything below 10 ppm methane. But for that, we can use the gas scouter, which has a fantastic precision up to about 800 ppm methane. And it also has the benefit of measuring CO2. But the drawback is that it can't go above 800 ppm methane. So we could have a miniature backpack explosion, which would not be good. And so what we're going to do is we're use these direct measurements that we have from these 3 different sources, and we use them to calculate emission factors, which we then multiply by activity data to estimate the annual methane emissions for Montreal from these 3 sources. And a quick note too, for Montreal's greenhouse gas inventory, much like other municipal greenhouse gas inventories, is that it does not break down emissions by gas species. It only reports them as a CO2 equivalent. So what we did is we used the methane emission ratios from Canada's inventory report to kind of estimate those equivalent methane emissions from Montreal's inventory report, because we have very comparable categories that we can use for that. Actually, in some cases they are, in most cases they are identical categories. So looking at the 3 sources that we're looking at, so historic landfills, manholes, and natural gas distribution, as you can see, they're broken up into all these different types of sources. So for historic landfills, we have the soil gas fluxes. We also have emissions from landfill vents, which you see here, this kind of J-shaped vent, and also observation wells. And you can see this picture at the bottom here is actually a park in Montreal, which happens to be the location of the historic landfill site. In fact, most of these historic landfills have been kind of either, I don't know what you call it, reconfigured into public parks, basically. In terms of manholes, we have 3 different types that we looked at: sewers, storm drains, and this other category that we have, which basically represents all manholes that were not identified as sewers or storm drains. This also excludes stuff like let's say manholes for fiber optic cables or for natural gas stations. So basically it kind of comprises this other category of manhole that we couldn't really identify. In terms of natural gas distribution, you see we have a breakdown of 7 different site types. I won't get into all of them, but I will note, especially at the bottom here in red, that we have 2 additional categories, these being third-party breaks and also pipeline leaks. Third-party breaks and pipeline leaks are essentially the same thing, actually, but the way to differentiate them is a third-party break would be a rupture to a pipeline that was, say, caused by, for example, a construction company. And these emissions are intense, they're very large, and they last for a short duration of time because they are reported, and then the local energy provider, in our case, Energier, who we're partnered with, they would go on site and actually repair these leaks pretty quickly. Definitely within a day, usually within an hour or 2. So looking at natural gas distribution stations first. So here's a chart of the 124 different natural gas distribution stations that we measured. This does not include the 81 third-party breaks that we had for 2020. We'll kind of look at those a bit later. In terms of a key takeaway here, I guess we could look at the highest site emissions that we're seeing are from natural gas gate stations. So specifically from pneumatic devices at these stations. And these are sites where natural gas is odorized, pressurized, and then kind of sent into the main distribution line in the city. So there's not many of them. There's only 3 in Montreal, but they end up having the highest emission factors. Looking next at historic landfill sites. So we performed a lot of measurements here, about 356, 340 of these being soil flux measurements, and also 16 from above ground infrastructure. So those wet wells and vents. Big takeaway here is that we're clearly seeing higher emissions from the landfill sites compared to our control sites, which you could call, in our case, we used as just public parks with no history of any historic landfill activity. We also noted some emissions from the vents and wells. I think on the upper level, we're getting to around 10 grams per hour, but nothing major. Another thing I'll remark for the historic landfill sites is that they were not spatially homogeneous. And this is common for many studies that looked at emissions from both active and inactive landfill sites. So the emissions are usually focused into these little hotspots. So they're not homogeneously emitting methane at the same rates. So it varies quite a bit. In terms of manholes, we measured 136 of them in the city. Big takeaways here that the emissions actually varied spatiotemporally. So that, what I mean by that is that in some cases for high emitting manholes, we revisited them and measured them again. And maybe one day we found they were emitting at around 10 grams per hour. When we returned, they were emitting at roughly 0. So they're changing depending on the time of day. And I'm sure the environmental conditions, the weather conditions, they all seem to have an impact. And also another remark I'll have is that we also observed higher emissions from manholes that were located within or very near these historical landfill sites. So that was an interesting finding, although I don't have any specific numbers to back that up here. It's more of an observation that we saw. And the highest emitting manhole we saw was around 33 grams per hour. And I can say that we've looked at manholes from other cities too. And what it appears is that this isn't the highest that we can get in terms of emission rates. We can see much higher emissions, and we can also see much higher emissions from many other manholes. So this may be an underestimation compared to what we're seeing from other spots, or it could be just representative of Montreal. Now, in aggregating all of these emissions, we want to compare them to Montreal's greenhouse gas inventory, which is what you see on the right here. So looking at this leftmost bar here, we have the fugitive emissions from natural gas distribution. So the top 2 contributors we can see are residential meters and these third-party breaks that I spoke about earlier. Now, residential meters don't necessarily have very high emission factors. In fact, I think they're emitting on average about 0.5 grams per hour, but there's about 100,000 of them in Montreal. So that's why you see such high emissions from them. Compared to third-party breaks, there was only, I think it was 81 events that we looked at, and cumulatively, they're contributing about 30 to 40% of overall emissions from fugitive sources. Now, in terms of the other 2 sources, we can see that for historic landfills and for manholes, that these are actually the 3rd and 4th highest methane sources in Montreal. These are, and together, they actually represent about 10% of the overall methane emissions from Montreal. So they're quite high, and this is significant, of course, considering that they are not considered methane sources in greenhouse gas inventories. And just for the last few slides, one really fun thing about this project was that we had really fantastic activity data. So for natural gas, we had the locations of every single station. We had all the pipelines. This is thanks to our partnership with Esg. And for the manholes, the city of Montreal actually keeps a record of all the locations of all these manholes in the city, including maps of the historic landfills that they have. So that's what leads to these interesting maps that we can create. And we can see how the spatial distribution of emissions looks. So for historic landfills, you can see these are localized to the locations of the landfills. They're kind of isolated compared to manholes, which are really spread out throughout the city. Of course, you have some pockets where there's higher density. And then if we look at natural gas distribution, One thing I want to note too is that natural gas distribution is on a log scale, because if you can see these tiny points of these these darker red dots, these are the locations of the third-party breaks, or also the locations of the gate stations, which had those really high emission factors. So really the emissions from natural gas distribution are kind of highly isolated to these specific areas. And if you consider third-party breaks, they're also isolated temporarily. So they're just occurring for a couple hours, basically each year. And they still contribute a significant amount of those overall emissions. I know I'm running out of time here, but just some quick conclusions. So Manholes, historic landfills, we found that there were significant methane sources in Montreal, and there's probably a good chance they are in other cities as well. The static chamber measurements that we performed here, they're fantastic for developing these actionable mitigation strategies, because not only do they provide accurate emission rate estimates, but you also have that extra confidence that you get in source attribution, because you're visually identifying the sites or visually identifying the site. Of course, this isn't the case in all instances, but overall, this kind of holds true. And in terms of future studies, they would definitely benefit from including or even focusing on these kind of direct measurements in their sampling strategies. It's just a valuable component to any kind of measurement plan. With that, I'll just go quickly to acknowledgements. Really like to thank Energia for all their help in this work, and also for funding sources, some references, and just for the video recording too, also the photo credits. So thank you. Any questions, please?
Thank you very much, James. There's already a question from Khalil. Do you suspect that old landfills emit more methane compared to newer ones? Does the age of the organic waste and/or operational practices affect emission rates?
Yeah, absolutely. These historic landfills will not be emitting as much as active landfills with that new fresh waste, because the organic matter is decaying over time. Basically, every year it's decaying. So some of these are over like 100 years old. A lot of that original organic matter that they had is now gone. So emissions from these historic landfills are going to decrease every single year. So that's when it gets interesting, when you start talking about potential mitigation, because it's very costly. It's going to be very costly to mitigate emissions from these historic sites. And it might not be worth it in the long run, just because those emissions are probably going to drop over time.
All right. See if there are any more questions. The only comment I might make about these landfills, having driven through a few of those plumes, even if methane might not be a core driver for overly costly mitigation, there were quite a lot of events that were really odorous in the middle of a city, which I think, is there any idea looking at other gases being emitted from those places as well that might have health impacts rather than just greenhouse gas impacts?
Yeah, absolutely. So I think I think this coming fall, we're focusing on a specific historic landfill site that has kind of been flagged as problematic. I think you might have heard about that one. And we are going to be looking at only H2S emissions, or the potential for H2S emissions from that site, but we're not really sure if we're going to see anything. But yeah, definitely. It's not just methane that, these sites, like why these sites are worrisome. There's also other pollutants and contaminants, and especially also effects towards groundwater, because there's no liners in place for these sites. So we don't even know what's going on in the subsurface.
And then Rasheen just added a question about, can we use those odor complaints to track methane?
Potentially, yeah, I think so. It'd be interesting if, I haven't really looked into this, but if City of Montreal has some kind of log of all these odor complaints, maybe we could look into it. Because there will likely also be odor complaints about natural gas, which has once it's odorized, has a smell that's a little bit more distinct from, let's say, the garbagey type of landfill smell that you might get. But it'd be interesting to look at, for sure.
Excellent. I think those are the questions we had so far. Thank you very much again, James, and everybody else presenting in this session. We now have scheduled a 15-minute break. I hope everybody is still awake or wants to grab a coffee or whatever they want to do. We have 6 more talks coming up after the break. I can promise aircrafts, models, data, everything your heart desires in the world of methane. With this, have a good break and see you at 55.